Welcome, everyone. We're diving deep today into quantum computing models, all these different fascinating ways that these incredible machines can be built and programmed.
Yeah, it's like we're looking at the early days of computers, back when things were just getting started. But now it's all about this crazy quantum mechanics stuff.
Yeah, exactly. And I think our listeners probably already know the basics of quantum mechanics. But how is quantum computing so different from like the computers we use every day?
It's all about qubits. So, think of a normal computer bit, like a light switch. It's either on or off, right one or zero. But a qubit is more like a dimmer switch. It can be on, off, or like both at the same time.
Oh, okay, so like a dimmer switch for information. I get that. But why is that so important for computing?
Well, because it lets these quantum computers, check out millions of possibilities all at the same time. It's like having millions of computers all working together at the same time. A normal computer has to go through each possibility one by one.
Yeah, that's what gives it the speed, right?
Yeah, exactly. It's that quantum speed up so it can solve problems in hours or days that would take our normal computers billions of years.
Okay, that's incredible. It's like having a superpower for computers.
Mm.
But how do we actually use this power? I know our source material mentioned the gate array model as one way.
Right. The gate array model is kind of like building a circuit, similar to the ones in your phone, but with a quantum twist.
Okay.
We use these things called quantum gates, and they're like little instructions to tell the qubits what to do. You string them together, and you get these complex quantum algorithms.
So it's like a choreographed dance where each step is manipulating these qubits to do a calculation.
Mm.
But how do we actually get from a bunch of manipulated qubits to an answer?
Well, we measure them, but here's the thing. You can wait until the very end of the calculation to measure.
Really? Why is that?
Well, think of it like this. When you measure a qubit that's in this both at the same time state, it's like bursting a bubble. It has to choose between being a 1 or a 0. But if you wait to measure it, you let it be in that weird state, that superposition for the whole calculation, and only peek at the result at the very end.
Oh, so it can explore all those possibilities at the same time until the very end. Okay, that makes sense. So we have these gate arrays, these quantum circuits that manipulate these qubits and keep them in this delicate state until the very end. But that's just one way to build a quantum computer, right?
Right. There are other ways, too. One of them is measurement-based quantum computing, and it's all about this crazy thing called entanglement.
Entanglement, yeah. That always makes me think of something spooky. What exactly is that?
Okay, so imagine two particles linked together, but they're linked in a way that even if they're super far apart when you measure one, it instantly affects the other one. It's like they're talking faster than the speed of light.
Yeah, that is spooky. So how does that work with computing?
Well, in this model, you start with a bunch of entangled qubits called a cluster state, and then you measure them in just the right way. And it's like you're teleporting the effect of a quantum gate onto those qubits.
Hold on, teleporting. Like Star Trek.
Not exactly. It's more like you're teleporting what the gate does, instantly changing the state of a faraway qubit.
Okay, that's still pretty wild. So we have these circuits and entanglement and teleportation all in quantum computing. This is mind-blowing.
Yeah, and we've only just started. There's another approach called adiabatic quantum computing. It's pretty different from the other two we talked about.
Okay, I'm ready for more. What's adiabatic quantum computing all about?
So think of it like a landscape with all these valleys and peaks, and your goal is to find the lowest point. You start with a simple system and slowly change it to one that represents the problem you're trying to solve.
Okay, I'm picturing this like vast quantum terrain. But how does slowly changing the system help find the solution?
Because the solution is at that lowest point, the ground state. And as you change the system gradually, it naturally settles into that lowest energy state, and that's the answer.
So it's not about like directly manipulating the qubits. It's more like guiding the system towards a solution by changing the environment they're in.
Exactly. And this approach is really good for optimization problems, like finding the best route for deliveries or figuring out the best structure for a complex molecule.
Like a quantum GPS for complex problems. This is incredible.
And there's more. There's another model that goes even further. It's called topological quantum computing.
Now that sounds like something straight out of Star Trek. What's so special about this one?
This one uses these weird particles called anyons. They're not like anything we normally see. They only exist in 2D systems, and they have these strange rules about how they interact with each other.
So it's even weirder than qubits and entanglement. Tell me more about these anyons. What makes them good for computing?
The cool thing is you can braid them around each other to encode information like you're weaving quantum information. And those braiding operations change the state of the system, and that's what lets you do calculations.
Wait, braiding particles, how does that compute anything?
It's a whole new way to think about computing. The way you braid these ennions determines the outcome of the calculation. It's like a choreographed dance where the steps tell you the answer.
This is amazing. I'm really seeing how each of these models is like a completely different approach to quantum computing. But is one better than the others?
That's a great question. And it brings us to the idea of the quantum Turing machine. It's like the ultimate blueprint for what a quantum computer should be able to do.
So the quantum Turing machine is like the ultimate quantum computer, the one that all the others are trying to be like.
Well, in theory, yes. And all the models we talked about, gate arrays, measurement-based, adiabatic, and topological, they can all theoretically do the same computations as the quantum Turing machine.
Oh, so they all have the same potential power.
In theory, yes. But just because they can do the same things doesn't mean they're all equally practical. Some models might be better for certain problems. Some might be easier to build.
Yeah, right? It's like different vehicles. You have a car, a truck, a plane. They can all get you places, but they're good for different things.
Exactly. And there's another thing that makes things tricky. It's noise.
Noise like static on a radio.
Kind of. Quantum computers are super sensitive, and any little interaction with the outside world can mess up the calculations.
So it's like trying to build a house of cards in a windstorm.
Yeah, that's a good way to put it. And that's why the computers we have right now are called noisy intermediate scale quantum computers, or NISQ computers.
NISQ. That sounds like a sneeze. But are those the ones we have now, even with all this noise?
Yeah, those are the ones we have now. They're still in their early stages, and they can't do as much as the fault-tolerant computers we want to build in the future.
So it's like we're working with the early versions. They have potential, but they're still kind of buggy.
That's a good way to think about it. But even with those problems, these NISQ computers might be useful in the near future.
So even though they're not perfect, they might still help us with some problems.
Exactly. They could be useful for things like materials science, discovering new drugs or solving really complex optimization problems. And researchers are working hard to figure out how to get rid of that noise and make them more reliable. There's some really cool research going on at Harvard about building error-correcting quantum circuits.
It sounds like we have a long way to go, but there's a lot of potential here. So it seems like we've covered a lot in this first part of our deep dive.
We have. We started by talking about what makes quantum computing so different from classical computing, and then we went through all these different models for building these computers.
Yeah, and we talked about this quantum Turing machine, which is like the ultimate theoretical goal, and then about the problems of noise and how researchers are trying to deal with that. It's amazing how many different ways there are to approach quantum computing.
Absolutely. And we're really just at the beginning of this whole quantum journey. We're just starting to understand how powerful these computers could be.
Wow. There's a lot to take in. I'm still trying to wrap my head around all those different models.
Yeah, there's a lot to unpack for sure, but it's exciting to see how each approach tackles these challenges in a unique way.
Exactly. You mentioned how different quantum computing models might be better suited for certain types of problems. Can you give us some concrete examples? I'm really curious to see how all this translates to the real world.
Absolutely. Let's start with adiabatic quantum computing, that one where you gradually transform the system to find the lowest energy state like we were talking about.
Right, the quantum GPS. So how would a company use that to solve a real-world problem?
Well, imagine you're a pharmaceutical company trying to develop a new drug.
Okay.
One of the biggest challenges is designing a molecule that interacts with a specific protein, the one that's causing the disease.
Yeah, trying to figure out how all those atoms fit together. That sounds super complicated.
It's a massive optimization problem with tons of possibilities to consider. A regular computer would take forever to go through all those options.
But an adiabatic quantum computer could use that quantum landscape to find the best solution much faster.
Exactly. It's like giving those researchers a shortcut to navigate through all those molecular possibilities and find the most promising drug candidates much faster.
Wow. So we could develop new treatments for diseases that are currently incurable. That's amazing.
And it's not just drug discovery. Think about materials, science, finance, logistics, anywhere you need to find the best possible solution.
So it's like a secret weapon for those really complex problems.
Mm.
What about gate-based quantum computing? What kind of real-world impact could that have?
Gate-based quantum computing, the one with the quantum circuits, is super versatile. One area where it could be huge is cryptography.
Oh, yeah. We talked about how quantum computers could break the codes that keep our online data safe. That sounds like a bit of a double-edged sword, a threat and an opportunity.
That's right. It means we need to develop new ways to protect our data. Quantum-resistant encryption. It's a race to see who can stay ahead, the code makers or the code breakers.
High stakes. What about other applications for gate-based quantum computers? Things that would actually help people not just protect us from hackers.
Of course. One area where it could really revolutionize things is material science. Imagine designing materials with specific properties. Like whatever you need.
Like materials that are stronger and lighter, or that conduct electricity better, or even materials with completely new properties we haven't even thought of yet.
Exactly. Imagine superconductors that can transmit energy with zero loss, or materials that can store energy way more efficiently. That would be a game changer for renewable energy.
It's like we're on the verge of a materials revolution, all thanks to quantum computers. What about those other models we discussed, measurement-based and topological quantum computing? Do they have specific applications too?
Well, measurement-based quantum computing, the one that uses entanglement, is still pretty early in development, but it could help us build more reliable quantum computers, ones that are less prone to errors.
It's like a more robust quantum computer that doesn't crash so easily.
Exactly. And then there's topological quantum computing with those anyons. It's a tough one to crack, but it could also lead to more reliable quantum computers, since braiding particles seems like a more stable way to store information than those delicate superpositions.
Right, it makes sense. What about neuromorphic quantum computing, the one that's inspired by the human brain? What could that be used for?
That's a fascinating one. It's basically combining quantum mechanics with ideas from how our brains work.
Okay.
It could lead to some crazy, powerful AI, systems that can learn and adapt much better than anything we have today.
So like building a quantum brain that can think like us, but with the added power of quantum mechanics.
It's a pretty bold idea, and it's still early days, but the potential is there. Imagine AI that can actually understand and respond to us in a natural way, or solve problems in creative ways, maybe even have some form of consciousness.
Now that's both exciting and a little scary. It seems like every model we've talked about has the potential to completely change different parts of our world. It's like we have this toolbox full of amazing tools, each one designed for a specific task.
I like that analogy. But like with any powerful tool we have, to think about the risks as well as the benefits.
That's true. We need to make sure we use these quantum tools responsibly and that we're ready for the changes they might bring.
What are some of the challenges and questions we need to think about as we move forward?
Well, one big challenge is scalability. Building quantum computers with enough qubits to solve really complex problems is a huge engineering feat.
Okay.
And it's not just about having lots of qubits, it's about making sure they all work together properly without getting messed up by all that noise.
So it's like trying to conduct a giant orchestra where every instrument has to be perfectly in tune and playing together. Yeah, something like that. And then there's the challenge of actually writing quantum algorithms.
Yeah.
The software that runs on these computers. We need new ways of thinking about programming to unlock the full potential of these machines.
It's not enough to just have the hardware, you need the right instructions too.
Exactly. We need brilliant minds to come up with these new quantum algorithms. And then there's the question of access. Will everyone be able to use these quantum computers, or will it just be big companies and research labs?
Right, that's important.
Right now, most quantum computers are accessible through the cloud, so that's helping to make it more accessible to researchers and developers, which is great.
So it's kind of like the early days of the internet, where only a few people had access at first, but then it became more widespread.
Yeah, I think there are some similarities there. As quantum computing technology gets better and cheaper, we can expect to see more people and industries using it.
That's pretty exciting. It sounds like we're on the brink of a quantum revolution, with these incredible tools slowly becoming available to everyone. But as we've been discussing, it's not just about the technology itself. It's about what it means for our society, our economy, even our philosophy.
You're right. Quantum computing isn't just a technological leap. It could change how we understand the world and our place in it.
That's a perfect lead into the next part of our deep dive.
Yes. In part 3, we'll delve into those bigger questions, the ethical and societal implications of all this. It's going to be a fascinating discussion. You won't want to miss it.
Okay, so we're back for the final part of our quantum deep dive, and I have to say this has been an incredible journey.
It really has, from those tiny qubits to these massive societal implications. It's been quite a ride.
It has. And we've talked about all this amazing potential, But now it's time to face the big question, the ethical and societal implications of all this. Where do we even begin?
Well, I think a good place to start is cybersecurity. We've talked about how quantum computers could break the encryption that protects so much of our digital world.
Yeah, that whole code-breaking thing, it's a little scary. It's like giving someone the master key to all our secrets.
It's a real risk, but it's not hopeless. Researchers are already working hard to develop new encryption methods that can resist quantum attacks.
So we might be able to stay one step ahead of the bad guys.
That's the goal, and it's pushing the field of cryptography in some really interesting directions.
That's good to hear. Okay, so maybe our data can be safe in this quantum future. But what about jobs? Will all these quantum computers put people out of work?
That's a question that comes up with every big technological shift, right? But history shows us that technology usually changes jobs rather than completely eliminating them.
So instead of worrying about quantum computers taking our jobs, we should be thinking about how they will change the way we work.
Exactly. Think about the Industrial Revolution. It didn't just destroy jobs, it created whole new industries and jobs that people couldn't have even imagined before. Quantum computing could be the same. We'll need quantum programmers, quantum engineers, even quantum ethicists. Jobs that don't even exist yet.
That's a good point. It's not about being replaced. It's about adapting and learning new skills for this quantum world.
Exactly. And that brings us to another important point, education. We need to invest in education and training so people have the skills they need for this new world,
Yeah.
Imagine if understanding quantum computing was as common as knowing how to use a computer today.
Yeah, that would be amazing. But let's zoom out even further for a moment. We've talked about data jobs and the economy, but what about the bigger picture? The philosophical implications. It feels like this technology could change the way we understand the universe and our place in it.
You're right. Quantum computing has the potential to reshape our entire worldview. Think about it. We could simulate these incredibly complex systems at a quantum level that could lead to breakthroughs in physics, chemistry, maybe even help us understand consciousness better.
Wow, that's getting pretty deep. It's like we're getting a whole new way of looking at reality, seeing the hidden quantum gears that make everything work.
It's both humbling and exciting. And, as we explore this quantum realm, I think we'll find more questions than answers, but that's part of what makes it so fascinating.
It's like we're standing at the edge of this uncharted territory, just starting to take our first steps.
And what a journey it's been. We've gone from these mind-boggling concepts like qubits and entanglement to talking about revolutionizing medicine and maybe even understanding the universe better.
And we see that with this power comes responsibility. We need to be careful and ethical as we develop this technology.
Absolutely. Quantum computing is not just about making better computers, it's about building the future. We want, a future that benefits everyone.
Well said. So as we wrap up this deep dive, what's the one thing you hope our listeners take away from all this?
I hope they realize that the future of quantum computing is not set in stone. We're all part of shaping what it will become. So stay curious, keep asking questions, keep learning, and explore this amazing quantum world.
I couldn't agree more. Thanks for taking us on this incredible journey. It's been an absolute pleasure. And to all our listeners out there, keep exploring, keep learning, and keep those quantum minds buzzing.